So last class, we just basically went over pretty quickly a bit about what a fluid is, defines fluids, how do we look at fluids, what are some of their properties. We looked at the difference between intrinsic and extrinsic properties. We talked about density, specific weight, specific gravity, and then I think we did 1 or 2 examples. So today is going to basically be an introduction and covering some of the basics of hydrostatics, or basically fluids at rest, if you will, or fluids not in motion. This covers a wide range of different types of problems, and a lot of them initial calculations or in some way involve hydrostatics, or the hydrostatic condition of fluids. So many fluid problems actually don't involve motion. An example here, just the water tower is essentially static and there's no motion, and there are forces associated with this that we need to solve for, different elevations, there's different pressures. Although it seems kind of simple, it can be a more involved problem than we think. So when a fluid has a zero velocity, the fluid, we consider it to be in the hydrostatic condition. So hydrostatics is related to pressure. Now, how is this related to pressure? If we just look at probably one of the more common experiments, if we have some cylinder, we fill it with water, and we perforate the cylinder, has holes where the water can escape. At different heights, we see that the velocity of the water jets at point 1, 2, and 3 here have different velocities leaving. These jets. So we have V1, V2, and V3. So we can see that the velocity is increasing as we go further down that water column, and that's because the pressure is increasing. And if we were just to draw sort of a diagram of what's happening here, let's say we have, let's make this a bit thicker. We have our wall, section 1, section 2, and hole 3, here's the bottom. So at this point, we would have some normal force N1. And then as we go further down, that normal force is going to increase N2, and then N3. And then for a little volume of fluid that will be flowing out of this region, there would be some shear force as well acting on this. So the fluid that is at rest beside it would be acting as some shear force, and the N values, the normal force, and these are basically the forces acting on this fluid as it's exiting. Now, I know I just said hydrostatics, and now I'm talking about water flowing out of these holes cut into the side of this container. But the point I'm driving here is that it is the pressure that is driving this behavior, and that pressure is hydrostatic pressure. So if we look at the volume or an element of fluid somewhere, some distance away, this is hydrostatic. Or we just say static, it's not moving. And it has some pressure P. And then the fluid that is moving, it's no longer static, but the force that is created by the pressure is what causes that fluid to leave that body with some velocity. So what is the relationship between this pressure inside this container? If we look at an element or a wedge of some material, or say a fluid element, how can we determine what that pressure is as a function of where we are in space? How does it change? So if this is our element here, we have our wedge. It has some angle theta that gives us the angle of this top phase here. let's assume that Z, positive Z, is our up direction. So that would mean that our force or acceleration due to gravity is downwards. And so the forces acting on this wedge of fluid would be some pressure in the x direction on the left-hand side, acting on this face. And that face is delta Z. We have some pressure Pz, and that's acting on the bottom face, which we'll say is delta X. And then we have some pressure Pn, which is normal to the face delta S. So we have those three forces due to the pressure. And then lastly, we have the weight for this differential wedge element, dW, which is equal to rho times gravity times the unit volume. So delta X times delta Z times 1/2, and times B, we'll just say B is the dimension into the page, and we'll just say it's a unit dimension. So if we look at this wedge, we've defined some forces, and the four forces acting on this are the three pressures Px, Pz, and Pn, and they're acting on faces delta Z, delta X, and delta S. And then there's also the weight due to gravity acting at the center of gravity of that wedge, and that's equal to rho g times 1/2 B, which is just a unit width into the paper, times delta X times delta Z. So if we write our equilibrium equations, this is hydrostatics, so the sum of the forces should be equal to 0 in each direction. So let's start off with sum of the forces in the x direction are equal to 0. And if we add up all the forces in the x direction, we have pressure, which is a unit of force per unit area. So we multiply that by delta Z times B. So we have Px times delta Z times B, and that's acting in the positive x direction. And in the negative x direction, we have the sine theta component of our normal force. So we have minus Pn times delta S times B times sine theta. And then this is all equal to 0. So that's our first equation. So let's now do the sum of the forces in the Z direction. Sum of the forces in the Z direction equals 0. There are three forces now acting in the Z direction. So the first one we'll count that positive upward force Pz times delta X times B. The other force is the cosine theta component, or the vertical component of our normal force Pn. So we have minus Pn times the area, which is delta S times B, times the cosine of theta. And then the last force is just the weight due to gravity. And that weight, dW, is equal to 1/2 rho g times delta X, delta Z times B. And this is all equal to 0. So we have this delta S sine theta and delta S cos theta component that is kind of a nuisance, and we kind of want to get rid of it. So if we look at the figure, we can relate delta S, which is basically the length of that angled section, to delta X and delta Z. And we can do that by saying delta S sine theta is equal to delta Z. Just using trigonometry, delta S times the sine of the angle between that and delta X is just equal to, delta Z. And then likewise, we can write delta S cos theta is equal to delta X. So if we do that, we can rewrite equation 1 and equation 2 just in terms of what do we call it, delta Z and delta X. So this term here, I'll write it in blue now, the top, can become Pn times B, a little hiccup, Pn times B, and delta S sine theta we said is delta Z. And then the terms down here, this can be Pn times B times delta X. So we have both of these equations now just in terms of delta X and delta Z and no delta S. So what we're trying to do now is basically rearrange and find what are the relationships with our PXs and PNs. So if we use equation 1, we can see that we have PX delta ZB minus PN delta ZB is equal to 0. So those delta ZB components, we can divide both sides by delta Z times B, and we'll end up with equation 1 simplifying to just PX is equal to PN. So we can write equation 1 again. Px is equal to Pn. So that normal pressure, Pn, is just equal to the horizontal component of our pressure, Px. And if we do the same process with equation 2, if we divide by our delta Z's, delta X's, we are left with our Z component of pressure, Pz, is equal to our normal pressure, Pn, plus 1/2 rho g delta Z. So equation 2, we're just simplifying, and we can get Pz, try and draw that a bit nicer, Pz is equal to Pn plus 1/2 rho g times delta Z. And then if we say theta is arbitrary and if theta becomes 0, delta Z becomes 0, and then this just basically collapses and then all those pressures are equal. So what we can write from this, from these two equations, is that there's no change in pressure due to motion distance or change in position horizontally, and there is a change in pressure due to our position vertically, and that's proportional to how far we move vertically, that delta Z. So there's 3 important characteristics of this hydrostatic condition from this analysis. So number 1 is that there is no pressure change in the horizontal direction. There's no pressure change in the horizontal direction. And that we just showed was from equation 1, Px is equal to Pn. In the vertical direction, the pressure changes proportional to the density, gravity, and the depth change delta Z. So in the vertical direction, we can say that the pressure changes proportional to the density, gravity, and depth change. Density, gravity, and depth. We'll call depth delta Z. And that was from the equation, our pressure in the Z direction is equal to Pn plus 1/2 times density rho times gravity times delta Z. And then lastly, if we said in that arbitrary condition that theta is 0, we can write that pressure is equal in all directions. Oof. So pressure is equal in all directions, and to make this a little bit more clear, pressure is equal in all directions for any given point in space. That doesn't mean that the pressure is equal at different heights or different elevations. It just means that at any point, the pressure is equal in any direction. So for any point in space. So that means if we had our wedge here, Pn, Pz, and Px, this was, sorry, it's not our wedge. So for the arbitrary case where theta was equal to 0, so let's just draw so this is a differential area, let's say. So it's a really small point. It's one point in space. Pn was equal to Px is equal to Pz. And then we can just call this pressure. Because it's equal in all directions, we don't really care whether it's Z, X, N, Y. They're just all equal to the same value, and we'll just call that pressure. Yeah, so the analysis above, we just chose a wedge. If we think back to our solid mechanics course and we wanted to find internal reactions, internal forces, and we derived the equations from Moore's circle, we basically did the same thing. So we have our stress in the X, stress in the Z, and then we have our wedge. We wanted to figure out the stresses. So for a solid, we wouldn't just have this normal internal force. We would actually have a shear force as well, right? So for a solid, we would have some shear component also acting on that wedge. But because this is a fluid, fluids can't support shear loads. The only forces acting on this wedge element are normal forces. And because of that, we get these properties. If we had the ability to sustain a shear stress or a shear force on an internal fluid element, then we wouldn't be able to get these equations. We would get our stress equations, our Moore's circle equations for solids. So these are essentially like the stress equations for a fluid or a material that can't handle shear stress. So a little bit more about pressure. Pressure is a single valued property at any point, and it's independent of direction. So it's not a vector. So pressure, we can say pressure is a singular valued property. So we can just call this a scalar quantity. And that is independent of direction. So that means it is not a vector. And that is, again, just reiterating that last line up above. We said that all of our components of pressure, our pressure directions, are just equal to P. So P is the same in any direction, so it doesn't really have any direction. Pressure is also a thermodynamic property of a fluid, just like temperature and density. So it's not a force, it's an actual thermodynamic property of a fluid. So pressure is a thermodynamic property of a fluid, just like temperature and density. It is not a force. So we can think of it as something that would create, is related to a force, but a force is a vector. A force has a magnitude and a direction. Pressure is not quite that, even though it is related. It has the same units as stress, but we think of it as a thermodynamic property rather than a force. Thirdly, a body or surface in contact with a static fluid experiences a normal force at each point due to pressure. So a body or a surface in contact with a static fluid experiences a normal force at each point due to this pressure. In contact with a static fluid experiences a normal force at each point and this is due to pressure. So pressure is not the force itself, pressure is the thing that causes the force. And then lastly, we'll introduce something called Pascal's law. So Pascal's law states that a pressure change occurring anywhere in a confined incompressible fluid is transmitted through the fluid such that the same change occurs everywhere. So a pressure change occurring anywhere in a confined incompressible fluid anywhere in a confined incompressible incompressible is really important here, is transmitted throughout the fluid such that the same change occurs everywhere. So what does this mean? Let's think of hydraulics, which we'll get into an example later. If hydraulics uses the concept of Pascal's law in order to create a mechanical advantage. So if we have an incompressible fluid, that means that you can apply as much pressure as you want to that fluid and it will not change its volume. It'll only change pressure. So you can take water, for example, and if we confine it in a container, so we think like a hydraulic system, it's completely enclosed, and we apply a pressure anywhere on that container, on that fluid, the pressure everywhere in that fluid is going to increase the amount that we increase the pressure at one point. And this is only true of incompressible fluids. So basically, a pressure change occurring anywhere, if we have a fluid that's confined and incompressible, the pressure change in one place will transmit and create the same pressure change everywhere. So this is really important for confined and incompressible fluids. It's not necessarily constant throughout because we have a pressure variation that changes with elevation, but for any point along the fluid that's the same elevation, then yes, the pressure change at the same elevation would react the exact same way to any increase in pressure. And again, this is for a confined fluid. So we figured out the equations for just determining that the pressure does not vary in the horizontal direction and it does vary in the vertical Z direction. Now let's actually find what the equation is. How does it vary? So if we have a volume element, or let's just do in 2 dimensions because we know in the horizontal direction it doesn't change. So if we have our differential element, and let's do the YZ axis this time. So this is our element. It is sitting in the YZ axis and it has some distance into the page in the X axis. And we can consider the forces acting on this element. One of them, the easiest one we can think of, would be the weight. And the weight would be rho times G times the volume. And rho times G is just our specific weight. So gamma times the volume of this element, delta X, delta Y, delta Z. So let's say that this face we'll call delta Y, this face we'll call delta Z, and then delta X into the page. And if this is a volume of fluid with pressure acting all around it, we can write differential form centered about the middle of all the forces acting, the pressure forces acting on this element. So the first one in the Z direction at the top, we can write as P plus dP dZ times delta Z over 2. And this is all times the area delta X, delta Y. At the bottom, we have P minus dP dZ, delta Z over 2, dx dy, or delta X, delta Y. On the left-hand side, we have P plus the gradient dP dy times delta Y over 2 times delta X, delta Z. And then over here, pressure minus the gradient dP dy times delta Y over 2, delta X, delta Z. So these equations are just the equilibrium equations for forces acting on a volume element. We have some pressure, and that pressure is changing as a function of, we're assuming it's changing as a function of X, Y, Z. So we can write the pressure on the left-hand side is equal to the pressure in the middle. So P is the pressure in the middle. So the pressure on the left-hand side would be P, the pressure in the middle, times or minus the gradient or the rate of change of the pressure with respect to the Y direction times however far away that side is. So that side is delta Y over 2 away from the middle. So that would be the pressure on that side. And the total force is that pressure times the area of that side. So delta Z times delta X into the page. And we're just doing the same thing for all of those. This isn't overly important, but I just wanted to show you that if you do a volume element or differential analysis, we can get these equations and then you sum the forces in the X, Y, and Z components to get the equations for pressure as a function of X, Y, and Z, assuming that they're changing. So before we do the sum of the forces, we can write some things that we know. We know that the pressure doesn't change in the X and Y and Z directions. Or sorry, the X and the Y directions. So pressure is constant direction. So this just means that our pressure change with respect to y dp dy. If we wrote this in the x direction too, it would be the same thing, dp dx. These are both equal to 0. So basically we can write these terms here, dp dy goes to 0, and this term here goes to 0. So if we sum the forces in the y direction, we would just see that the p times delta x delta z minus p times delta x delta z is equal to 0. So that summation isn't really going to help us too much. So let's look at the z direction. The z direction, we have the force due to gravity. So that's going to change. The dp dz is going to be related to the amount of material we have in between and the force of gravity. So if we write the sum of the forces in the z direction, similar to what we did before, these are all equal to 0. We would end up with p minus the partial derivative of p with respect to the z direction times delta z over 2 times, we'll just call delta x delta y is just the area, delta A, minus p plus partial derivative dp dz delta z over 2 dA, and then lastly we're going to subtract gamma times the area delta x delta y, so dA delta z. So if this equation is equal to 0, we can basically divide out all of the like terms. So every single one of these terms has a delta A, so we can divide out delta A. Every single one of these terms has a delta Z, so we can divide out those. And if we rearrange all this and put it back together, we can isolate dP, and dP is equal to negative gamma times dz. Or another way we could write this is dP dz is equal to negative gamma. So what does this mean? Well, remember what gamma means. Gamma is our specific weight. So gamma is equal to rho times g. So the rate of change of our pressure with respect to the z direction is equal to negative rho times g, or negative gamma. So if our density is constant, if we have an incompressible material, so we can't change our density with pressure, and if our acceleration due to gravity is constant, then we can integrate this quite easily, and we would get an equation. So if gamma is constant, then we end up with the equation P2 minus P1 is equal to the integral of 0.1 to 0.2 gamma dz, which is just equal to negative gamma Z2 minus Z1. So this is if our pressure is constant. So let's just rewrite this. We assume that we have an incompressible liquid with a constant gravity field. So basically, we can say rho is constant and G is constant. And let's rewrite this. We can, from that equation, we can write pressure P2, or the pressure difference between any 2 points, P2 and P1, is equal to the negative integral from point 1 to point 2 of the specific gravity times, or the specific weight rather, times dz. And for a constant case, this becomes P2 minus P1 is equal to negative gamma times the position, the z position, Z2 or Z2 minus Z1. Another way we could write this equation is we could write it as the z position at any point plus the pressure at that point divided by the specific weight is equal to the elevation, or the z at any other point, plus its pressure divided by the specific weight. So what does this mean? What does this mean physically? Let's just imagine we have some container some jug, and it has water, and we know the pressure at the surface. We can just draw that. Pressure at the surface is P air. Maybe we can say P air is equal to 101 kPa. So if we have a point 1, 2, 0.3 on that container, and let's assume it's filled with our fluid, we can relate the pressures at any 2 points by looking at the difference in their directions, or the difference in their position in the z direction. So we can say in a continuously distributed uniform static fluid, the pressure varies only with the vertical distance and is independent of the shape of the container. So it doesn't matter where you are in the x and y direction, it only matters where you are in the z direction. This also works for an enclosed container. Now the enclosed container, the difference might be that if we were to put a lid, let's put a cork, a green cork in here, the pressure at the top of that fluid, when we put it right to the top, might not be the same as the pressure of the air. It might be some other pressure, but the pressure at the top would be equal to some pressure. Now, the pressure at the top of the fluid could just be another point. It could be 0.4. So we can relate 0.1, 2, and 3 to that 0.4 using these two equations here. Well, they're the same equation, to determine the pressure anywhere in that fluid if we know the pressure and the elevation of some point. And then we know the change in elevation of another point with respect to that point that we know the pressure at. So if we know pressure at one point, we can find pressure anywhere else in a static, incompressible fluid using this equation if we just know the change in elevation z between those 2 points. So we can say, just in summary, in a continuously distributed so that means there's no breaks in the fluid, there's no barriers stopping it. and it's all the same fluid. So a uniform static fluid, it's not flowing. The pressure varies only with vertical distance. And it's independent of the shape of the container. The next thing is that the pressure is the same for all points on a given horizontal plane. Is the same for all points on a horizontal or a given horizontal plane. And a caveat here is this is in the same fluid. So that's if the fluid isn't changing. So let's sort of look at a concept here. So in this diagram, we have some oddly shaped container. We've got atmospheric pressure at the top free surface, and we have depth 1 with points A, B, C, D, and we have depth 2 with points capital A, B, C, D. And the pink section is water, and the gray section is a different fluid, and that's mercury. So we can write, if we look at the left-hand side over here, we can look at the pressure distribution for a water column going from the bottom to the top. And the pressure would increase from the top, and it would increase linearly. And the slope of that increase would be equal to the specific weight of water. So we can say that the pressure, for example, if we were to just draw this, this would be the pressure distribution as we would travel further down this column. And we could say that dP dz is equal to negative gamma, which is the specific weight of water. So let's look at the other side now. Let's look where we have our fluid change. So we said that the equation from before holds true as long as we have a constant fluid. So if we have our water column going up on this side, we would have our pressure change, we'd have the same slope as on the other side for within the water. And then at the point where the fluid changes, the slope isn't constant anymore. It's going to change with respect to the specific weight of mercury. And mercury is much heavier. It's much more dense than water, so it's going to have a higher specific weight. So the slope of this now changes. And let's do this in red maybe. So our slope would then look something like this, where this pressure is increasing much more rapidly because that coefficient gamma is much higher in mercury than in water. So over here, we still have dP dz is equal to negative specific weight of water. But then once we change to mercury, our dP dz is now, or the slope, the change in pressure with respect to our change in Z is proportional or equal to the negative specific gravity of mercury. Mercury. Excuse me. Okay. So if we know this now, how can we relate the pressures at these different points? Is this statement true? If I write pressure at A, lowercase a, is equal to the pressure at lowercase b, is equal to the pressure at lowercase c, is equal to the pressure at lowercase d. Is this first statement correct?
Yes, because they all have the same amount of water above them.
Yeah, so they have the same amount of water above them. It's a continuous and uniform fluid, so the fluid's not changing. It doesn't matter what the shape of the container is. They're all in different shaped containers, but it has nothing to do with the shape of the container. It only cares about the change in depth, and they're all in the same horizontal plane. There's continuous water connecting them, so we can draw a line continuously connecting all these points without traveling through a barrier or a different kind of fluid. So we can say, yes, that's good. So yes, the first statement here, the pressures at lowercase a, b, c, and d are all equal. What about the other point? Let's write the pressure at A is equal to the pressure at B is equal to the pressure at C. Say that's capital C is equal to the pressure at D. So is this equation correct? No. So why isn't this, what do we need to change to make this expression correct? Right, so we can draw a continuous path between all of these points, A, B, and C, but we can't draw a continuous path anymore because we have this mess. We changed to mercury. It's not uniform. It's not continuous anymore. So we can't say that A, B, C, and D are all equal, but we can say that A, B, and C are equal, but they're just not equal to D. So we would just write is not equal to D. So pressures at A, B, and C are the same. Pressure at D is different, and that difference we drew over here is because we have a change in our material. So a specific weight is, like we said, specific weight is our density times acceleration due to gravity. And if we're using SI units, that's usually given in units of newtons per meters cubed. And then this is just some common specific weight or specific weights for some materials. So water is pretty common, is 9,790 newtons per meter cubed. And we can see mercury is significantly higher. So a change, if we have a container of static fluid, if that fluid is water, the pressure at the bottom for the same height of the fluid would be a lot less than if we had a fluid container filled with mercury. So a higher specific weight means that the increase in pressure as you go down into that fluid is going to increase faster. Another thing we need to talk about is something that I think gets confused a lot, and this is the difference between absolute pressure and gauge pressure. I notice I spelled gauge wrong. Gauge pressure. So absolute pressure is the, exactly as it sounds, it's the pressure of a fluid relative to zero pressure. So absolute zero means that you're in a vacuum. You have no pressure at all. Pressure is equal to zero. And gauge pressure is the difference between the pressure that a fluid is experiencing, the absolute pressure of a fluid, and the atmospheric pressure. So we can write pressure P gauge is equal to the absolute pressure minus the atmospheric pressure, or PATM. So if we look at this diagram here, this is showing, I'm not actually sure what this diagram is showing. Maybe the next slide will help. I kind of forget my point with this slide. The main point here we wanted to make was that our gauge pressure is basically the difference between the absolute pressure and the atmospheric pressure. A lot of times when we're referring to pressure of something, we're usually referring to the gauge pressure. We're not referring to the absolute pressure. So the gauge pressure is just your pressure relative to the atmospheric pressure. So a great example, case where I come across a lot is if you're riding a bicycle. So you have your bike tire. And your bike tire might say, if you have a mountain bike, maybe you're inflating it to 30 psi, or road bike, you're inflating it to 120 psi. The pressure rating that has is your gauge pressure, and you're reading it literally on a gauge. And that gauge is just measuring the difference in pressure between what is inside the tire and the atmosphere. So pressure of the tire that you would read is equal to gauge pressure. And this would be equal to, I guess, your absolute pressure. So the absolute pressure of that minus your atmospheric pressure, so 101 kPa. So because generally speaking, the atmospheric pressure is pretty constant, we just assume that there's not much variation in our atmospheric pressure, and so we don't really care about our absolute pressure. We just care about this gauge pressure, and it's a lot easier to actually read, and then it can actually simplify a lot of our calculations. So the main thing is, remember that our gauge pressure is the absolute minus the atmospheric pressure. So hydrostatic pressure distribution in oceans and atmosphere. So another thing we need to keep track of when we're doing these pressure variations is being mindful of the convention for direction. When we're talking about fluids can be liquids or gases, and the convention for where we choose the free surface and that coordinate of z is equal to 0 at the top of that free surface. So at this free surface, this line right here, z is equal to 0. So for our equations, we would say that the pressure, if we look down below, if this is maybe a lake, we have water in the lake, the pressure at some depth minus h, or some direction minus z, is going to be equal to the atmospheric pressure, which is the pressure at the top. So we'd say PA plus h times the specific weight of water. And in this case, h is negative because we're going downwards from that free surface. If we have, now looking up into our gas environment, so we're going into the atmosphere, we have air. Our pressure is equal to the same equation, P plus the distance B, and B is now going to be positive, times the specific weight of air. So as we go down into water, we're going to increase our pressure because that H is negative, and then as we go upwards, we're going to decrease our pressure. All right, does gravity change significantly enough in deep parts of the ocean to not be able to be treated as a constant? So gravity may change to I think we'll get to this in a bit, but the effect of gravity as we get closer, say, to the center of the Earth, or we get deeper, deeper. So think we're in the deepest part of the ocean, maybe Marianas Trench, or kilometers down, gravity might be different, but that doesn't really have an effect on the specific weight or the density of the fluid. It would be still quite minimal, maybe like 1% or 2%. A much larger effect on that would actually be the temperature. So even though the fluid is incompressible, that just means its density doesn't change too much with pressure. But it does have a significant effect and change with temperature. So let's just do a quick example on static pressure variation in a lake. So Halls Lake, it's a freshwater lake in Ontario, has a maximum depth of 80 meters and a mean atmospheric pressure of 101 kPa. Estimate the absolute pressure in kPa at this maximum depth. So basically we have a lake. It has some depth at the bottom, which is 80 meters. And it says the atmospheric pressure is equal to 101 kPa. So what is the absolute pressure in kPa at this maximum depth? So why are they adding P atmosphere? I'm not really sure where you're referring to. Are you referring to here?
I'm just referring to both the P, where the positive B, you're adding the air pressure, and you're also adding the water pressure. But shouldn't you be subtracting the air pressure on the positive B?
Yes, I think you're right. Whoops. Yeah, that is a minus sign. There. Okay, so it's asking you to estimate the absolute pressure in kPa. So we're going to assume for this problem, because we don't have any information, we're going to assume that temperature is constant. What else are we going to assume? We're going to assume that the specific weight, we'll assume the values for water, which we set up above, was 9790 Newton per meter cubed. So what we can do is we can write pressure at the bottom. So the max pressure is going to be equal to the atmospheric pressure plus H times gamma. So in this case, now we're going downwards. So it ends up being negative Z. So we can write PA minus 80 times 9790. And PA is actually equal to 101 kPa. So if we do this, do we have to fix something first? Is this correct? If we were to plug in these numbers, would we get the correct answer? Right. We have units of kPa here. You can't have kPa. We need to write this in terms of pascals. Pascals is newtons per meter squared, so we have to make sure we have the same units. So 101 kilopascals is 101 times 10 to the 3 pascals. So we can write it 101 times 10 to the 3. And that gives us pascals minus 80 times 9790. So if we do that, 9790 times 80 minus 783 I think I wrote the equation wrong. So it's minus h times gamma, and h is in the negative z direction, so it's minus 80. So this should end up being a plus. As we go down, we're increasing that pressure. To me, that's more easy to remember than this convention. If we're going downwards in a fluid, the pressure should be increasing, and if we're going upwards, pressure should be decreasing. So this pressure should increase our pressure. We should have a positive pressure, and it'd be 101,000 plus 783,000, which give us 884.2 kPa.
Would it be possible to go over the equations in the previous slide? Because I'm getting confused on what the correct equations are now.
Okay. I love how one of the textbooks has this figure and it says, be mindful of the convention. And I find it also confusing. So just think of it this way. Whatever you're going to choose for your value, choose z is equal to 0 as your reference. And that's always going to be the free surface, or the surface of your liquid, where liquid and air meet. And whatever equation you choose to use, just know that pressure is increasing as we go down. And pressure is decreasing as we go up. So all this equation is saying here is maybe the main equation would be pressure is equal to PA plus minus Z gamma. This is the equation that is probably easiest to use, assuming that Z is equal to 0, and that corresponds to your atmospheric pressure, or your pressure at that free surface. This is just a simplification for when we're talking about bodies of fluid or water open to an atmosphere. This was just an equation. If you ever get confused with this, you can always go back to these equations here. I like to just think of these ones because these are much easier. And if you're looking at P2 versus P1, just assume one of those positions, maybe P1 is equal to your Z of your atmosphere. So if we look at this top equation here, P2 minus P1 is equal to negative gamma times Z2 minus Z1. P1 can be our atmospheric pressure, PA. So we can rewrite this. P2 is equal to PA minus gamma Z2. And if we choose our reference Z1 at the open free surface to be 0, then it's just minus 0. So we just have this equation. So that's all this is happening. And then later on, we're getting over here and we're saying, okay, typically we will use the variable h to represent a depth in a liquid and the variable b to represent the altitude in atmosphere. But I'm fine if you don't want to remember this equation because this might be just more confusing. If you remember those two equations from above, then it always makes this easier to solve. And then it's much less likely that you would make a mistake. Even I made a mistake right here because I do find it confusing. So I would prefer to solve using P2 minus P1 is equal to negative gamma Z2 minus Z1. And then what we can just do is say P1 is equal to PA and Z1 is equal to 0. And Z2 is equal to minus 80. And we get the same answer. So I might find this may be easier.
Thank you, that was helpful.
So now that we've gone through that, let's do another example that might be a little bit more confusing. So the figure shows here we have an access hatch at the end of a service pipe, or maybe there's some sort of equipment that needs to get into some column of fluid to take measurements. When the water reservoir is full, the absolute pressure at A is 400 kPa. If the atmospheric pressure at the access hatch located at B is 100 kPa, determine the resultant force the reservoir water and surrounding air exerts on the hatch. The inner diameter of the pipe is 1 meter. Or actually, that's, yeah, 1 meter. So let's first draw what exactly this is telling us. So we have our reservoir, there's some access, and we know that on the hatch, it is open to the atmosphere on the other side. So the pressure on this side of the hatch is equal to the atmospheric pressure, 101 kPa. And we know the pressure at point A point capital A, the pressure over here is an absolute pressure of 400 kPa. So it's asking us to determine the resultant force the reservoir water on the surrounding air exerts on the hatch. So what we need to look for basically is if we solve for the pressure at B, pressure that we solve for at B is going to be the absolute pressure. And then we'll have a pressure from the fluid acting on B, and we'll have a pressure from the atmosphere on the other side acting at B. So we have to find the net pressure, which would be the gauge pressure. And then once we find that, we can calculate the actual force acting on that hatch by multiplying the pressure by the area of that hatch, and we know the diameter is 1 meter. So let's find the pressure at B if we know the pressure at A. And we know the dimensions in the Z direction, 0.3 meters. So let's write our equation. Pressure at A minus pressure at B is equal to negative gamma, specific weight of water, ZA minus ZB. So if we rearrange this, we can rewrite this as pressure at B is equal to the pressure at A plus gamma water times ZA minus ZB. We know gamma of water. We know pressure at A. What will be the value of ZA minus ZB? Is it positive 0.3 or negative 0.3? Right, negative 0.3. Pressure at B, since it's at higher elevation, it's higher up from point A, so it should have a decreased pressure. So if we're going to decrease the pressure from point A, that means that the quantity inside the brackets, ZA or ZA minus ZB, should be negative. So that'd be negative 0.3. So we get 400 kPa, 400 times 10 to the 3, plus the specific weight of water, 9790, times negative 0.3. We get the pressure at B is equal to 397 times 10 to the 3 pascals. So if we take this and we multiply by the force, what is the force at B? So remember, the force at B is going to be the net pressure. So it's going to be the pressure from the fluid acting at B minus the pressure of the atmosphere at B. That would be our net pressure. And because the pressure from the fluid is greater than our atmospheric pressure, the force should be pointing upwards. So it would be pressure at B minus pressure at A times the area, pi over 4, and it gives us diameter, right? Times 1 squared, or diameter squared. So we get 397 minus 101 is pi over 4 times 1 squared is just 1 times 10 to the 3 because we're dealing in pascals. And we would get an answer of, I don't actually have the number in front of me. Does anyone have a quick calculator? $232.5. 232.5. Good. Or sorry, kPa. What are the correct units? This is the unit of force. We have pascals times meters squared. So it should be newtons, yes. 232.5 newtons. Good. Let's take a quick break. When we get back, we'll talk about head pressure and some more properties of static fluids. So let's give it a 5-10 minute break. Let's meet at 10 after 1.